Hey guys, today we're going to talk about 7.2, more talking about standard deviation, and also introducing you to some words, variability and consistency. So, consistent is an athlete or team's performance when they're very similar to each other. So if a goalie blocks about the same number of goals each time, or a golfer hits a ball about the same distance each time, we say that he's consistent. So, think about if you were taking a test. If you're consistent with getting A's, that means all your test grades are around an A. So where would your average be if you're consistently getting A's? Well, your average would be in the A's. So similarly, we can calculate that standard deviation. So how far away each data point is from the mean. And you'll notice that when you're comparing two data sets, if one of the sets is smaller, has a smaller standard deviation, then it's considered more consistent. So if you were looking at a bunch of your test scores, and you range between a 90 and a 100, okay, so say these are your test grades, okay, versus if your test scores range between a 70 and a 100, okay, the dots really don't matter. But you'll notice that this right here has a smaller spread. So standard deviation is a measure of spread. So standard deviation is a measure of spread. So if you have a smaller spread, that means your data points are closer together, whereas if you have a larger spread, your data points are further apart. So if you have a smaller standard deviation, you're more consistent. If you have a bigger standard deviation, you're less consistent. Now the other vocab word that I'm going to introduce you to is variability. So the more variability you have, the more spread out your data is. Versus the more consistent you are, the more condensed your data is. So here, in this example, versus this guy, we have more variability because our data is varying more so from the mean. So more variability, and we are less consistent. Now on this bottom graph, you have less variability, and you probably already telling yourself that means you are more consistent. That's because your data is less varying from the mean. So let's say if we're looking at two different graphs, you're trying to decide what the White Sox manager, Ozzie Guillen, complained that his team had lack of consistency. So what was the lack of consistency? What was going on? And the lack of consistency is in the runs allowed. So in runs allowed, there is a greater standard deviation. So I don't even have to check the standard deviation to see that if I'm ranging from 1 to 12 versus from 2 to 7, that standard deviation is going to be bigger. So you have a greater standard deviation, which means you are less consistent. All right, they were slightly more consistent with runs scored, but really, if you're thinking about a manager, you can kind of start to visualize what your data would look like, what you'd want your team to be. So you would want your teams to consistently be maybe within this region for runs allowed, because that way they're allowing less runs for their other opposite team to score. And you may want runs scored to be a little bit higher, but still consistently falling between two areas. So let's say you have this raw data. So if I give you a list of data and I ask you who is more consistent, the way that you calculate consistency is by looking at the standard deviation. So I went ahead and put my data into the calculator. So you're going to have to know how to calculate standard deviation either by hand or using the calculator. So for Curtis Martin, his standard deviation is, this standard deviation, and I'm again looking for SX because SX is the sample standard deviation. This is just a sample of his overall ability. So the sample standard deviation was 30.27. I always round decimals to the nearest hundredth. Now for Sean Alexander, his standard deviation is 50. 0.66, okay? So which one of those was more consistent? Well, you're looking to see which one is the smaller one. So we have Curtis Martin's more consistent. Because he has a smaller standard deviation. That means that Sean Alexander has more variability. So there's a bunch of different things that you can say in terms of the consistency and the variability. So think about it with yourself. If you were, or with with your parents, ask your parents, if you were a team manager, would you rather have someone who's more consistent or a team that has more variability? Let's say I am a hockey manager and I am looking at goals, the amount of goals that my team makes. And let's say that my team consistently makes between 0 and 3 goals. Would I rather have that, or would rather my team score between 0 and 15 goals? Do I want a team that has the potential to score really high numbers, or do I want a team that I know the expectations? So this kind of leverages a really interesting conversation. Which one is better to have? So another thing that you could do is you could look up different sports teams, say which one is more consistent, which team was a better team, and analyze it based on the standard deviation. As we get further into this unit, you're going to see that normal distributions and calculating z-scores is going to be one way that we can compare our two players or two students. So it's kind of taking different contexts, putting them on the same playing field and saying, really, which team is better? So this standard deviation is just one way to measure it. All right, this next part is a little bit tricky. So here's a dot plot of Kobe Bryant's point totals for each of his 82 games in 2008, 2009. The mean of his distribution is 26.8, and he has a standard deviation of 8.6. Okay, so this is kind of the backbone of what we start to introduce with the empirical rule. And I don't really want to say that too much because I want you to discover and see what's going on here. But if I ask you, in what percentage of his games did he score within one standard deviation? So I find the mean. The mean is 26.8. And I'm going to add a standard deviation above and subtract a standard deviation. So a full standard deviation away from the mean records lower and the upper. Like if you add a standard deviation above and a standard deviation below. So that is one full standard deviation away from the mean. So I go to my calculator, 26.8, and I'm going to subtract the standard deviation of 8.6. That gives me 18.2. And then I'm going to take 26.8 and add 8.6, and that gives me 35.4. So between 18.2 and 35.4, so 2, 4, 6, 8, 18.2, I'm going to say maybe falls right here. And then 35.4 is one standard deviation. And I have that there are 82 games, so there's total 82 dots. And I'm going to count all the dots within there. So I have 1, 2, 3, 4, 5, 6, 7. So there are 57 games between 18.2 and 35.4. Now, if it asks what percentage of the games did he score within one, you're going to take 57 and you're going to divide by the total number of games or total number of dots, which is 82. So 57 divided by 82, that is going to be 69.51% of his games within one standard deviation. Okay, now if I want to find how many within two standard deviations, I'm going to start at those boundary lines that I just created. And I'm going to subtract a second standard deviation, and I'm going to add a second standard deviation. So I'm going to go 18.2 minus 8.6. That's going to give me 9.6. And I'm going to do 35.4 plus 8.6. That'll give me 44. And I'm going to draw those boundary lines. So essentially, within two standard deviations, I am subtracting my standard deviation and I'm adding two standard deviations. So I'm finding 9.6, 9.6 right here. And I'm finding 44. 44 is 2, 4 right here. Okay, I could count all the dots within, but instead I know that there's 2 dots outside, so it might be a little bit easier this time to say if we have 80 games between 9.6 and 44, which is 80 out of 82. So that's 97.56, 97.56%. So you're going to be calculating these percentages a lot. But what I want you to notice is the shape of this distribution. So what are we seeing that this shape is? Is it symmetric? Is it skewed right? And I'm seeing these 2 values right here. And I'm thinking, are these outliers? So we can kind of almost calculate and see if we think that they're outliers. Not necessarily calculate without the actual raw data. But we can kind of think about them maybe potentially being outliers. So that means, is my data skewed right? So you're going to be recognizing in the next couple days that there is a pattern with the data when it's skewed right versus symmetric. But make sure that you know how to calculate 1 standard deviation away from the mean, 2 standard deviations away from the mean, because that's going to be really critical moving forward with your normal distribution. All right? Let your teacher know.